dive in here. So let's talk about what do we mean by the term cloud native. So when you go out and search for the word cloud native, you'll find lots and lots of different definitions, lots of blog entries or articles on the topic, and they're all kind of different. So you kind of have to pick your reference sources a little carefully. There's a open source open consortium called the Cloud Native Computing Foundation, and they're as good a source as any. So they are trying to foster a community that drives cloud native best practices, as well as kind of vendor neutral tool choices, and primarily focusing on open source. So they really want to drive adoption of cloud native technologies. And the best way to do that is to have most of the tools be free and have them be stable and robust and supported by big companies and so on. And so that's what the Cloud Native Computing Foundation is all about. And you can go to their website and browse around. They've got a tremendous amount of material there, and actually we'll cover it a little bit in this section. But when you look at how they describe cloud native, this is their definition here. This is just taken directly from their site. And you'll notice they don't actually talk about any tool choices here. In fact, the word Docker is not mentioned. Kubernetes isn't mentioned. Other open source tools aren't mentioned here. What they're talking about here are the best practices and the outcomes that companies are starting to realize when they move towards a cloud native approach. So really it's about building applications in a certain way. So some of it is about application architecture choices, things like using containers, or I'm sure most people have heard about microservices and good APIs. And so it's primarily about that from an application building point of view, but really it's about how do these cloud native applications take advantage of what is called cloud native infrastructure, meaning orchestrated container management platforms. Kubernetes has basically won the container orchestration platform battle. A couple years ago, there actually was a battle. There's Docker Swarm and some other choices, but Kubernetes has really won that battle. So that they could actually say Kubernetes here, but they don't. But basically, it's how do your applications take advantage of what Kubernetes has to offer, and that is by building your application in a way that it can be resilient. It's got good observability. You can do proper CI/CD and DevOps and deploy frequently and so on, and scale, and all the good stuff that you see kind of the best of breed applications out there in the world doing today. Kind of unlimited scale and so on. But for us, when you kind of search across all the definitions, it really comes down to a couple things here. From a technology point of view, it's microservices, containers, and some orchestration platform. And as I mentioned, that's Kubernetes. But from a best practice point of view, it really does mean, in some cases, a culture shift, if not a process and tool overhaul for development teams. You want to start adopting more open technologies, and especially integrating into open technologies. As we'll see later, there's some logging and monitoring tools in Kubernetes that are extremely popular, Prometheus and Grafana, for example. And if you don't integrate with those, you're going to be left behind. So there's a part of this that it almost impels you to understand the open landscape and plan your integrations accordingly. But it's also about automation, real DevOps, real CI/CD, and so on. So I'm not going to go through this chart. It's a bit of an eye chart, but it's us trying to say, given our current portfolio and our customer experience with our portfolio, what benefits can we hope to derive, or can we measure ourselves against as we start to move parts of our portfolio to become more cloud native? So, most of the things on the left here are things that our customers struggle with today and kind of where they'd like to be. So rather than have, our products have a specific set of system requirements where they can only run on, version X of this operating system, really eventually you want our offerings to run on generic cloud resources wherever possible. And in this case, this means Kubernetes and the cloud native space. So this means having our software be runnable on day one in generic Kubernetes infrastructure. Being able to easily combine and discover and try out all of our capabilities. Again, this gets back to the catalog, which we'll see in SoFy. So yeah, I'm not going to go through this whole list because, but it's a thing we spent some time on. Back on the Cloud Native Computing Foundation. So one thing they realized very early on is that people were struggling to understand what it meant to actually get on the road towards cloud native for their own applications or their own environments. And so what they've done is they maintain this thing called the trail map, sort of a graphical representation of 10 things that you could be focused on if you want to start to move towards cloud native. And they're not saying in this chart that you need to focus on all 10. It's more of a strategic view of here's 10 things you could be focusing on. But the first one is always the first one. Containerization is sort of table stakes for all of this. This trail map is supposed to, as I said, provide a kind of a bunch of milestones or goals that you could be thinking about. Containerization, as I said, is always step one. And as we'll talk about when we talk about the HCL portfolio and how we're trying to modernize it, it really is step one. You focus on containerizing something, and then you can focus in on some of the other aspects. And so you can see some of the items here, CI/CD. So this is really about making sure you're set up to do proper delivery and actually taking advantage of the fact that, you know, once you've built a container once and you've got that into your DevOps pipeline, it actually makes CI/CD so much easier. As we'll see when we get to the bit on Docker images, just the act of containerizing something makes it that reusable asset that can flow throughout your DevOps pipeline and provide really reusable, robust capability in any environment because you know it's a packaged version of something that contains all the dependencies it needs and it's going to run anywhere the Docker can run. Orchestration, this is basically Kubernetes. In fact, they say it here, Kubernetes is the market leader. Observability analysis, this is one of the key aspects of cloud native applications, is the ability to say, it's not just about deploying an application, it's about how do I manage it day to day. And so today with our legacy applications, each of them has their own logging capability. Some of them, you know, will do syslog, or some of them will do some log aggregation or other things. There are technology approaches in cloud native where people are plugging into existing logging frameworks. And as I said earlier, the expectation from customers is it's gonna be not that we come with our own logging capability that they've got to learn and figure out and integrate into their own day-to-day system reliability engineer process. It's going to be more about how do we integrate into what they've already got. And usually that's based on some of the common tools in cloud native for monitoring and logging. There's some other things here, service mesh. We'll talk about that a bit. That's more of an emerging topic, which is basically a cluster level thing you install to control and monitor more closely how your services inside your cluster are talking to each other. The other ones are, you know, networking, database, messaging. For us, these last two here are really important. So the container runtime, this is about what Kubernetes is using to run your containers or how your cluster's set up. But software distribution, this is the big one for HCL. How do we actually deploy containerized versions of HCL software to end users? Customers who are doing Kubernetes and Docker expect there to be registries that they can point to that have all the images they need and get pulled down dynamically as needed when things get deployed into their Kubernetes environment. So for us, this is a big thing we're trying to help solve with the SoFy project, is how do we do cloud native software distribution in HCL? Okay, so one thing that we've also done, and this was done at the level of the product management team, is we're trying to measure where we currently are in our portfolio. And again, we wanted to keep this measurement activity as simple as possible. Obviously, we're not going to measure ourselves on those 10 things that we just saw on the trail map. That would be far too much, far too granular. For our purposes, we can measure things much more simply. In fact, we boiled it down to these 3 things: containerization, orchestration, and cloud native maturity. So basically what this means is the product containerized, or do you have a service in your product that you can containerize? If so, you get a check mark for that. Once you've got and actually we'll see this in the Docker hands-on section. Once you've got your stuff containerized, the next question is, can you run in Kubernetes? And just getting your container running in Kubernetes is good enough really to get a check mark. If you can run there, that's great. People can stand up your product probably much more simply than they can today, because they can run a few commands and get your product stood up inside a cluster. The last piece here, cloud native maturity, this is where this is about applications fully taking advantage of what's available both in Kubernetes and in the industry leading tools like the logging and monitoring and other things. So basically, this last piece here is kind of the nirvana. So that's really what this last thing is about. It's about, we've containerized, we can run in Kubernetes, but now we're taking advantage of all the goodies it has to offer. Okay, so the next section, I'm just going to talk a bit about Docker. For those of you that have played with Docker, this will be complete review. But I'll go through this as quickly as I can, but not try to skip over it too much, because it really is the foundational technology for everything we're doing here. So understanding what Docker images and containers are is very important. A few things we like to stress for folks that are just getting started is understanding upfront what's the difference between a container and a virtual machine. It's actually one of the first things I had to wrap my head around a couple of years ago when first getting into this space. We'll talk a bit about the architecture, but not too much, one slide. And then the key terminology that you need to know if you're going to do anything with containers specifically. And then I'll show you some stuff in action. As I said, this won't be a hands-on part, but I'll show you how to install the Docker desktop tools, and you can try all this yourself if you want. It's actually really, really useful, especially for development teams, but also if you want to manage your own demo environments locally or something, you can containerize things and manage them that way. Okay, so what is the difference between a container and a virtual machine? The answer is really about where the abstraction layer lives. So with VMs on the right here, it's really the physical hardware that's being abstracted away so that you get full copies of an OS and everything on top of it running on the same host. And so I'm sure everyone on this call is very familiar with VMs, so you know how those work. The difference with containers is the abstraction layer is actually a level higher. Containers are not full operating systems. They are, the abstraction layer is basically the application level. And so containers actually share host resources. They share networking, they share storage, they share users, other things, but they have their own isolated view of all of those things, their own namespaced view. So container A thinks, so when it's running, when you have a process running in container A, it thinks it's the only thing on the system. If it does system calls to say, give me all the users or show me all the processes running, it only sees itself. It only sees stuff that is inside its own container. Same thing with container B and container C. And so it's a level of isolation and it's a level of sharing on the same host that's much different from VMs. And the important thing to note here is this means because there's not a full copy of the operating system in every container, they're much smaller and they start much more quickly. So the best mental model to have about what a container is, it's not an operating system running lots and lots of stuff. A container is really a process running on a host. So typically a container will just run one main process, and when it's done, it'll exit. Or if you're running a server, it'll run a long running process, but that's it. Its job in life is to run a process. But to do that, it can have its own view. It looks like it's running on a full operating system, but it's really not. So that's the difference, and we'll see this in action a bit in a second. The Docker architecture, I only show this because if you start to work with Docker, you might wonder about some of these terms. So starting on the left, the Docker client, so typically all of your interaction with Docker is going to be with the Docker command line tool. So it's the primary client that you use to interact. And when you run Docker commands, you're talking to what's called a Docker host, or sometimes called a Docker engine. And that is usually local. And so when I show you what I'm doing here, I'll show this all local. So I run Docker commands, and it's running and starting and stopping containers on my system. But that Docker host doesn't necessarily need to be on the same machines. That's why it's pictured this way as different boxes. And images are, and we'll talk about what images are in a second. But containers or images are stored in a registry, and so these are places where it's just like our current FlexNet. It's places where people get the images from. And and what's special about Docker is it has a special API to push and pull images from a registry, and it does it in a very unique way. Actually, I won't get into it. I'll show you. It'll be much more understandable once we see it in action. So before I show you things, let's get a few terminology pieces squared away too, because this is a common source of confusion as well. The terms image and container are kind of used probably too much and not the right context. So an image in Docker speak is the read-only template for how to run a container. Yeah, an image is thought of as a file, a read-only file. And when you run that image, you're actually creating a container. And so the container is the runnable thing. And I'll show you what that looks like when we do the Docker demo in a second. If you get into the business of building your own images, you do that quite simply, and I'll show this also, with a Docker file. And the typical flow is this. You have a Docker file, you run Docker build, that will build a new image, and then when you run it, you're creating a new container that's going to be running. If folks could go on mute, that'd be great. I'm getting some feedback from when I talk. Okay, so I'm gonna do a quick demo here. As I said, you should be able to replicate all of this if you just download Docker Desktop. These are some of the commands we'll run, and I'll show you quickly what each of them does, and hopefully you'll get a sense for what people do to get started with Docker pretty quickly. Okay, so let me switch over to my browser here, and I'm gonna see if I can make this bigger. Hopefully you'll be able to read this. Okay, so let's get started here. So actually, before I do this, let me just show you Docker Desktop. So I'm on Windows here. I installed Docker Desktop, and again, you just Google for it and you'll find it. But what you get is a kind of a long-running application here. And once you install it, you get the core commands you need. You get Docker command line. You actually get kube control as well. And you can start to do some interesting things in here. You can actually run your own local Kubernetes cluster, which is something they've added recently here. And you can actually do a lot of Kubernetes playing all local on your laptop if you want. But basically, this gets you all of the capabilities. What this is really doing under the covers and is running the Docker daemon, and it's giving me a Linux environment that all of my containers are going to run on, a virtualized environment. And so it's hiding all the gorp away from me about having to make sure there's a Docker daemon running. And it just lets me get started super quick. So as I said, you install Docker Desktop, and right away you'll have access to things like the Docker command and so on. So let's see it in action. So out of the box, when you first start, there's a few commands you can use to poke around. You can say Docker images, and this is going to show me what images, what files, what images from a registry do I have local. And here I have none, because I actually cleaned everything out before we started this demo. So I'm starting completely fresh here with a brand new system effectively. So I've got no images. And if I wanted to see if I have anything running, the command to do that, some people ask why it's not Docker containers. It's actually Docker PS, which stands for process status. And again, this gets back to the point that the best way to think about a container is not a whole operating system running. It's really a process that's running on your host. So when I run Docker PS, I should get nothing as well. I have nothing actually running at the moment. So the simplest thing to do is let's run a image and create a container from it. If I just do Docker run hello world, let's see what happens here. I'm going to scroll up here and we'll see what it did. So when you run, so Docker run will do a few things. It'll see if you've got whatever image you've referred to here locally, and if not, it'll go try to pull it from a public registry. And then it'll also create a new container and then start that container for you. So you can kind of see that in the output here. So the first thing it did, it tried to see, hey, is there hello world with the latest version locally? Nope, there isn't. So then it went and pulled it. And in this case, it's pulling from docker.io, which is a public repo that Docker maintains with millions of images that you can play with. And we'll see a couple others when I do a bit more here. But it pulled it, and then it ran it. And so this output here came from the Docker. And so really what it did, it just printed out this hello world, and it printed out some other stuff here. So now if I do Docker images, after I've done that Docker run, I'm going to see now I have a local image that was pulled. You can see some metadata here. Whoever created this created it 14 months ago. You can see it's tiny. And this is the latest tag. Now, interestingly, we ran that container, but if I do a Docker PS, which again means show me the containers, I see nothing. And that's because the image, in this case, ran its process and terminated. So I can say Docker PS show me all containers, not just the ones that are running. And this is going to show me the hello world was created about a minute ago and exited about a minute ago. And so I have this container now with its own ID and so on. And so that's kind of the easiest way to get started, is running some previously created images from Docker Hub. And actually, let me just go there for a second. I'll just show you what you get. So if you do go to Docker, you can just search for Docker Hub. You'll land in a place like this, and you can search for content. You know, I can search for, actually, I don't know if I've searched for HCL in a while. There probably won't be much on here because we're not putting our images here because we want to have our images all in a protected registry, but you can search for anything in here. So if I wanted to search for MongoDB or something, I can find lots of stuff. It's tagged by how many downloads have happened. You know, people can star images, so this provides sort of a reputational type of approach to this. So you can only, if you wanted to only download containers that have lots and lots of downloads and have stars, then that's probably a good approach. But each of these entries in here, if you click on it, it's going to tell you how to do what I just did with Hello World. Actually, let's do that. Let's go to Hello World, the one I just ran, because that will be, I think, more instructive. So this is the one we just ran, the Hello World. When you go on one of these entries, you'll see they'll usually give you some pretty good instructions. In this case, it's telling me the exact Docker run command I should use, and so on, and lots of other information. And there's versions of this image. If I was on, you know, for example, my Raspberry Pi, and I wanted to run this on the ARM architecture, I would run a slightly different command. I would tag it with ARM or PowerPC or lots of different architectures that this thing can run on. Okay, so let's do something a little more interesting, because running a Hello World is really not that interesting. So I am going to use a different container. I assume most people on this call are very familiar with web servers and web applications, since DX is one. So I'm going to create the most simple web application you can have. So this is a local HTML file I have. Obviously, it does nothing other than print out a heading. And so if I want to quickly run this in a real application server, Docker is really, really good at this. So I can take any of the app servers that I know about, you know, Open Liberty or Tomcat or JBoss, and I'll be able to find an image for those in Docker Hub. Freely available. I can kind of do whatever I want with. So I have this script that's a one-liner, and it's going to run my little web app that contains nothing but an HTML file, and it's going to run it in Open Liberty in a container, and we'll see that in a second. So I'm just going to break down this command a bit because it's a little bit more involved than the previous Docker run we saw, but it's doing some interesting things. So this first part here is called port publishing, or some people call it port mapping. What this is saying is when I looked at the documentation for Open Liberty, it told me that when I deploy my apps here, by default, Open Liberty is going to expose port 9080 for traffic. And so that's, again, because every container has its own isolated view of everything, including network, that port is actually not available to my local host, even though I'm running the container on the same machine. So I need to publish that port to my local host. So in this case, I'm going to say, yes, it's port 9080 to WebSphere, but on my local host, on my Windows machine here, when I run it, I want to access it on this other port. I could have chosen the same port. I could have said 9080:9080, but just to make it different, to show there's an ability to change that, I use a different port here. So we'll see what that looks like when I actually run it and access it. The important part here is this -v, which is doing a volume mount, which says, take this local file path, in this case, it's where my index.html lives, and map that or mount it inside the container at this location. And so the way this works is Open Liberty is always looking in this folder it knows about, config drop-ins, for anything that's new. And so by running this command, it's going to create a new folder in there called myapp.war, and that folder is going to contain this index.html file. And then I'm also giving my container a name because that makes it easier to run subsequent commands against it, like starting and stopping it and other things, which we'll see. And then the last piece here is, what is the image that I want to use? And again, this is just from Docker Hub. You can search for Open Liberty. You can find all kinds of images and various flavors of it. But that's it. This is the command where I'm going to run my application here in Open Liberty. So let's see, I'm in the Docker. Yeah, so I'm just going to run this. This is going to, I'm going to start to see some output here. I mentioned earlier that Docker images are pulled by layers. That's what you see happening here. So the Open Liberty image that I referenced is made up of several layers. And so what's happening here is each of those layers is being pulled locally to my machine. A new container is being started, and now it's in the process of starting up. So now we're starting to see some Open Liberty logs. Anyone who's played with Open Liberty will probably recognize these. And so my app's starting up here, my process is starting up, and it looks like we're good to go. So I've got the server is ready to run a smarter planet, which is what Liberty usually says when everything's up and running. So if I now go to my browser and I go to localhost, and if you remember, we mapped it to port 9082. If I just go there, I'm going to see, yep, I've got Open Liberty running, and by default, Open Liberty will create a path to the app here. So this is now running in a container, but it's serving up content that actually lives on my local host, because this volume mount, it's not a copy of the file. This is actually, the container is referencing the file on my local disk. And to show you what that means, if I go back to my local file system here and I change this and save it and go back to my browser and refresh, the changes are live. So even though this is in a container running in its own isolated network with its own set of things, because I did that volume mount, it is actually sitting on top of that local file system. So this is one of the reasons Docker is so tremendously powerful for development teams in particular. If I want to develop a new web app, or actually a new application of any kind, I can have the code local, and I can have all of the language specific stuff in a container. So I don't need to pollute my Windows machine here with, for example, Java installs or Node installs or any other installs for language dependencies. I can put all of that in a container. I can run it, start it, stop it, and still have my code local and use my favorite local editor here. So this is one of the first things that development teams really latch onto as a key value of containerization. I'll just stop there. Does it make sense so far? Any questions or confusions? I'll take silence as a no. Okay. So, but let's do something more interesting. So, let's say we've built up our application that we. Oh, and actually, let me do one other thing. I'm going to create a new. I'm going to Control C in my current command prompt to get my command prompt back. This did not kill the container. This just killed my attachment to the container. So now if I do a Docker PS, I'm going to see, I don't like the way that's going onto a separate line. Maybe I'll make it a bit smaller. Hopefully that's still readable. But yeah, so Docker PS now is showing me actually there is a running container now. Here's the image it's based on. It was created 3 minutes ago. It's been up for 2 minutes. I can see information about the port mapping. So, I wanted port 9082 locally, and that's pointing to port 9080. That name I gave it in the command with the -- name, that's what makes it really handy. So for example, for any running container, I can do things like this now. I can do Docker logs, my app, just show me the running standard out logs that have been accumulating since it started. And that's one of the nice things about Docker and Kubernetes is they sort of automatically retain logs for containers for the long haul. So this is the full set of standard out logging that Liberty did. So at any point you can get to that. Also, again, if I do, let's just go back and do Docker images. Now we'll see I have 2 images locally. I've got that one from the Hello World we did with the first run, and then now I've got my Open Liberty local again. So now if I run another Docker run with Open Liberty, I'm not going to incur any of that download cost. This image that's been cached locally here is going to be used for my next container that I start with Open Liberty, which is one of the things that Docker really shines at, is this local caching and quick development turnaround. Okay, so some other things you can do just quickly here. If you want to follow the log, so let's say you've got a long running application and you're interested in what it's doing, you can do Docker logs -follow. And this is going to sit there. And if there's a new log entry that Liberty spits out, it'll show up here on my command prompt. So it's basically a way to watch what's going on, which is also helpful. Really helpful for troubleshooting is maybe if you're the developer of this image and something's not working and you want to get in and see what's going on, Docker exec is one of the most powerful tools that you can use. So it means execute a command inside your container and do something. So the most simplest way is to do something like execute in the container my app. I happen to know inside Liberty there's a server XML in this location. So show me the output of that server XML. So that's it. So this is going into the running container and running this Linux command. And so I can run anything here. I can do ls and just show me what's in the current folder and so on. Even more powerful is I can run an interactive shell with -it, and I can say run bash. And this is going to land me now in a shell where I'm actually in the Liberty container, and I can poke around as if I'm fully logged in. And so now I can do lots of interesting things right here at the command line, like I'm inside Liberty. So that's really powerful, obviously. And then I just exit to get out of that bash shell. One last thing is, let's say there's some configuration file or something inside Liberty that I want to get out and pull locally, so I can open it in my nice editor here. There's a Docker CP or copy command. So you do something like this. You'd say Docker my app, config server XML, and then the place you want to store it locally. So I could say cached server XML, and that's going to go into the container, and you can see it's already copied it locally here, but this is going to grab that file and store it locally on my file system so I can go do things later. So lots and lots of troubleshooting help that you can get. Oh, one other thing I'll show you, which is useful, as I mentioned, Docker containers really are about running a process. So you can run the Linux command top, and they actually provide that as a top level Docker function here. And when I do this, Docker top, it's going to show me the processes running in this container. And this is going to show me from a Linux point of view what actually got invoked when Liberty got started. So I can see the full command line here. It started up a Java process and set some Java properties, and here's the exact setup. So again, if you're in the business of a container, this is something you'll probably be interested in. Okay, so let's say now I'm happy with my web application. Now I want to actually package this thing up. I want to package up my fancy web application here into its own image so that I can ship this to users and they can just do a Docker run, not worry about volume mounting, just do a Docker run and have my app pre-deployed in Open Liberty. That is about as simple as it can get. So for that, we need a Docker file. As we mentioned earlier, a Docker file is basically it's a simple text file with a bunch of commands in it that tell Docker how to build up an image. And so in this case, this is about as simple as a Docker file can get. You can get much more complicated than this, but in this simple example, we're just doing exactly what we did in the Docker run command. We're starting from a base image, the same one we used in Docker run. And this time, instead of volume mounting, we're copying our local file here, our local folder, into that same location that we previously did a volume mount to. And so this is going to, and to build this thing, I would just, let me see, am I in the right folder? Yep, Docker files here. So to build a new image is, again, just a one-liner. You say Docker build, you give it the folder where your Docker file lives. In this case, it's in my current folder, so I just say dot, and I tag it with some name. So I can say my app version 1.0.0. And that's it. So this is now going to go, it's going to make sure, because again, we set up here from Open Liberty Web Profile 8, it's going to make sure it has that image locally, and then it's going to go build my new image, and we're done. So if I say Docker images now, we can see in my local cache, we now have the image that we just built, my app version 1.0.0, created 6 seconds ago. You know, not surprisingly, it's the same size as the other one because we added almost nothing to the Open Liberty, but this image is now runnable on its own. So I can do this now. Docker run, I'm going to do -d this time, and I'll show you what that means. It means detached mode, which is a different way of running images, but also helpful. This time I'm going to map a different port. So we'll do, let's say, 9081 to 9080, and we're going to give this container a different name. We'll call it myapp2, and then we do the image that we want to actually run. So it's the image we just selected. So I run that, and it should be up and running. In this case, you'll notice we didn't get any of the Liberty logs or any of the other starting up logs. That's because of this -d flag. It means run in detached mode. It means return immediately to your command prompt, but behind the scenes, the container has been started up and so on. So if I now do a Docker PS, I'll see actually now I have 2 running servers, and one's at port 9082, one's at port 9081. If I go now to my browser and go to 9081, I'll see it's also running there. And the difference now is it is actually using content that's been copied into the container. So if I change my file back to Jeff here and save it, this one will stay as Mary because it's the one we just deployed with the packaged version of the app. If I go back to 9082, the one we started with, it's going to be what I just changed it back to, Jeff. Right, so and this again, so this is the next flavor of really interesting value that developers get out of Docker. I now have 2 versions of the same app server running on my machine, completely isolated from each other. So this is really valuable when you want to replicate, for example, an older version of the product you're working on, or you want to maintain demo environments of previously shipped products. You can just store images of anything you want and run them. Oh, and I didn't show you start and stop. So at any point, I can do a Docker stop, and we'll stop the one we just started. My app 2, I think I called it. Yeah. So now if I do Docker PS, we'll only see the one we started initially. If I do a Docker PS-A, we'll see the one we stopped in here. And now I want to show you one thing that's interesting. If I start that one we just stopped again, I don't have to specify all of that port mapping stuff. That's persisted as container configuration. So once I've created a container once and given it a name, I just start it like this, and it will start exactly the same way it started before. And there's a really interesting piece about the logs that I'll show you here too. If I now get the logs of my app 2, we're going to see 2 sets of logs. We're going to see the original set that was from the first time we started, and then the second set, all because again, Kubernetes and Docker persist all the logs from container restarts. So you know, if this container started 10 times, I would see 10 sets of logs here. So really, really useful for troubleshooting and so on. Okay, so I didn't want to spend too much time on Docker. Hopefully that gives you a flavor for what you want to think about if you're going to try it. I would highly suggest, if you've got time, install Docker Desktop and start playing around. One of the really exciting things about this space, Kubernetes and Docker, is because so many people are doing it, there's so much to find on the internet. It's just a Google search away. All kinds of interesting uses of this that I didn't even touch on, that in lots of different ways of leveraging the technology. So, okay, so Kubernetes. Once a development team, because usually the way Docker and Kubernetes get started in a company, it's usually not from an executive mandate. It's usually from some curious development team getting started with Docker and seeing the value, and then it grows from there. And the way it grows is, as soon as you've created one or more containers, you start to ask these types of questions, which all lead to Kubernetes. Things like, okay, well, what if I containerize my web app and I containerize my database? How do they talk to each other? Or how do I, if I've got multiple containers, do I have to script all of this Docker start stuff and start them independently, or is there a better way to do that? And so on. So lots of questions like this, as I said, all lead to Kubernetes. And so I always show this chart, and I only show it because I want to make sure people don't see this in the wild and get scared away from Kubernetes. If you Google for Kubernetes, you more often than not land on a chart like this. And you, as an end user of Kubernetes, you need to know almost nothing about this chart. This is the underlying architecture of Kubernetes. And so under the covers, when you deploy a cluster, this is what happens. And so each of these things over here in the node section, each of these is essentially, think of it like a VM with a whole bunch of stuff running. Kubernetes calls them nodes. But the fact that the process that Kubernetes runs on a node is called kubelet or kubeproxy doesn't matter to you. So if you ever land on charts like this, feel free to just ignore it, and we'll talk about the stuff that matters on the next couple slides. So for real end users, what you're usually doing, and we'll show you this, is you're doing a declarative approach with Kubernetes. Kubernetes is a really interesting platform. Its goal in life is to take in configuration from you, where you're telling it, hey, I want the system to be in this state. And the state can be things like, I want to make sure there's 5 versions of my, or 5 copies of my container up and running for scalability purposes, or I want to install this application or something, some state. And Kubernetes is always listening. And when you make these kind of changes, and you do that by applying new YAML into the system, and we'll see what that looks like. When you actually do this, Kubernetes wakes up and says, oh, there's new configuration, and then it goes off and does a whole bunch of work to get you into that state. So the reason it's kind of a declarative approach is you're saying, here's the desired end state, and Kubernetes will eventually get you into that state. So it's not like you sit and wait necessarily for your end state to be perfectly golden. You're basically telling Kubernetes, here's where I want you to be, and go do all the work required to get there, which could be installing containers, starting or stopping other things. And the real value of Kubernetes is if something goes wrong in the future when you're not looking, like some pod or some container fails or something, it will then wake up again and try to get you into the desired state. So if one of your containers, one of your 5 somehow fails, it'll try to restart it automatically to get you back, always trying to get back to that desired state. So the key objects that you do need to know about if you're going to do Kubernetes are listed here, and there's some others, but the key ones that we're going to wrap our heads around here are pods and services. I won't talk about namespaces much, but deployments and others. So we'll see these in action in a second. And one of the really nice things about Kubernetes, which I just mentioned actually, is even if you think that as you're trying to deploy something to Kubernetes or try to solve some production grade challenge with your application, so many people have already paved the way here. So most challenges that you think might be unique to your product are typically already solved in some way, and they're usually just a Google search away. One of the real powers of sitting on top of open technology is there's just so much resource out there to borrow from. Okay, so rather than start from the top down or from some bunch of words to describe what the core objects are, let's try to do it graphically. And I like to build from the bottom up, because most people come from a basic understanding of Docker and containerization. And so Kubernetes takes that and abstracts it away and adds a whole bunch of other abstraction layers to make the system work. So let's talk about what those are. So let's say we've built a container that maybe surfaces some REST API. So maybe it could be exactly like that Open Liberty container we just built, but instead of hosting a web app, maybe it just serves up a REST API. And that's all it does. And maybe it's stateless. It can come and go. It just serves requests and returns results. What Kubernetes does, there actually is no object in Kubernetes called a container. The lowest level of abstraction in Kubernetes is called a pod. And a pod is basically a runtime environment for a container. You can have multiple containers in a pod, but usually the best mental model is just think of a pod sort of roughly equals a container. So in this case, to deploy my REST API container to Kubernetes, I'm going to wrap it in a pod object, and we'll see what that looks like. A pod gets its own IP address and its own port, so it's addressable inside the Kubernetes network by other things. But the really important part about pods and actually containers in general is the best way to think about them are to think about them as completely ephemeral. So Kubernetes makes no guarantees that it's going to try to keep your specific pod here up and running. In fact, based on what's going on in your cluster, it can decide to shut it down, restart it, do all kinds of things to it. So you need to build your containers as if they might get killed and restarted at any point. And so that means, and when a container or a pod is killed, that means all the data inside that container's file system goes away. So if you do have persistent data, obviously most useful containers do, those need to be handled separately with persistent volumes in Kubernetes, which we'll talk about in a second. But as you're building your containers, you think about them as ephemeral. They can come or go, someone can delete them, restart them based on what's going on. So, but just deploying one pod on its own is really not that interesting. All you're doing is really deploying your container to Kubernetes, and that's not much more useful than doing it on your laptop and deploying one container or running one container or doing a start like we did. So Kubernetes has a really useful abstraction called a deployment. There's other flavors of this called replica set and daemon set, which we won't get into, but The basic one is a deployment, and a deployment says you're gonna deploy one or more replicas of a given pod. And so what you can do with the deployment is you can say, actually, I want 2 copies or more. You could have 100, but in this case, I want 2 copies of my pod available at all time. And you declare that in your deployment. And again, that's just more YAML, which we'll take a look at. But the key object here is, from a Kubernetes point of view, is the deployment. It says, here's the pod, here's the image to use, and make sure you've got 2 of them running at all time. And each one gets its own IP address and its own port that it exposes traffic on. So the problem is, if you were trying to build some service that consumed or tried to call this REST API, the problem is now your service needs to know these IP addresses and ports. And again, these can come and go. Think of them as ephemeral. So maybe tomorrow 10.0.0.2 is not going to exist. There's going to be a new one because that pod was killed and restarted. So that's just chaos for someone trying to call this REST API. So Kubernetes comes along with yet another abstraction called a service. And in this case, a service is the persistent endpoint, IP address and port that exposes pods, function in pods. So now it's not the individual pods that you're talking to, it's the service object. And again, pods can come and go, and because they all have this label, and this is the magic that hangs it all together, and we'll see this in the YAML file, but each pod says, here's my label. In this case, it's a simple label, my app. And the service says, I'm essentially serving all pods that have that label. So that's how it knows what pods it can use to direct traffic to. So for example, if 10 more pods get stood up with that label, now the service has 10 more pods it can direct traffic to. And again, this IP is still internal to the cluster, the service IP, but it is persistent. So it is the long-running thing that consumers of this function can depend on. Okay, so now we want to expose our traffic to clients outside of the cluster. So everything to this point has been internal cluster IP import. If we want to expose something externally, Kubernetes has a concept of an ingress, and this is where you can have various types of fronting services, but you can expose, for example, a public IP address and port, and you can route requests based on the incoming HTTP request to various services. And you can have more than one based on the incoming request or URL. So in this case, the clients of this function, it's just like any other web application. They're communicating with a public IP address and some known REST API format, for example, but they have no idea that behind the scenes this is Kubernetes and there's services and pods exposed. So the ingress is really the thing that that clients connect to. I mentioned I mentioned earlier that stateless is kind of what we're talking about there. It's the easy approach. When you do have containers that need to persist data, so for example, if Kubernetes decides to shut down my DX container and I don't want to lose all my data, all of the stuff that's considered part of the user data or generated data in DX needs to be persisted. So that's done with a couple other abstractions. One's called a persistent volume and one's called a persistent volume claim. So Kubernetes has intentionally abstracted away from pods how their storage is provisioned and managed. So all a pod does is says, I need some storage that meets these requirements. And so in a persistent volume claim, a pod will say something like, I need this type of storage, maybe NFS or something, and I need 80 gigabytes or something like that. So it's making metadata claims or requirements against the storage, but has no idea how that storage is going to be provisioned or managed. Kubernetes then sees a new persistent volume claim and we'll go try to see if there's existing storage providers configured in the cluster to support that claim. And if so, it'll go do that provisioning, or you can do it manually, but Kubernetes will do it dynamically if necessary. And it will bind that back in. So from a pod's point of view, when it starts up, it has a persistent volume claim. It says, I want some storage of this type, and I want to mount it at this location in my file system. And when it starts up, it has no idea how that was done. It just knows that there's a file system there to start interacting with. And when that pod goes away, it's the same pod configuration that Kubernetes is using to start up again. So it's that same persistent volume claim. So that's how pods can start and restart and have access to their persistent data. Hope that makes sense. It's a really complicated topic, actually, once you start to dig into it. And so this is one of the things we work with most of the product teams on to try to figure out the approach here, especially taking legacy apps, which have kind of important files stored all throughout the file system, or important files stored, and trying to figure out how to do proper persistent volume mapping. Okay, and before we start doing the hands-on part, I wanted to talk really quickly one slide about Helm, because we will be using that. So as we'll see when we start doing the hands-on, deploying stuff to Kubernetes is really, really low-level configuration file-based interaction. So you're typically editing YAML files, which are not that easy to read or edit, and you're deploying those things and reading and writing them from the cluster. So Kubernetes a couple of years ago, in combination with some other people, came up with Helm, which is their default package manager. Now it's off on its own project. And a Helm chart, which is what the term they use for basically an application bundle. A Helm chart is really just a big tarball of Kubernetes YAML files that make up an application. So it gives the end user a simple way to install what could be a arbitrarily complex application made up of dozens of different YAML files that some of them are hundreds or thousands of lines long. The end user is just doing a simple one-line Helm install command. And so we'll see that, and we'll see what that looks like.